Welcome back. This is the 9th video in our 10-part series on quantum computing. Previously, we discussed quantum error correction. Today, we'll explore the different hardware platforms used to build quantum computers.
Professor, I'm curious. Are all quantum computers built using the same technology, or are there different approaches?
Excellent question, Sneha. There are actually several different hardware approaches to building quantum computers. Let me show you the 4 main platforms. First, we have superconducting qubits. These use Josephson junctions and are the technology behind IBM and Google's quantum computers. They operate at extremely cold temperatures near absolute zero.
Professor, when you say extremely cold, just how cold are we talking about? And why does it need to be so cold?
Great question, Arjun. We're talking about temperatures around 15 millikelvin. That's colder than outer space. This extreme cooling eliminates thermal noise that would destroy the delicate quantum states. The second major platform is trapped ions. Companies like IonQ and Honeywell use individual ions trapped by electromagnetic fields and manipulated with precisely controlled laser beams.
Wait, you can actually trap individual atoms in space. How is that even possible?
It is incredible. We use carefully designed electromagnetic fields to create a potential well that holds the ions in place. Then we use laser pulses to manipulate their quantum states with remarkable precision. Third, we have photonic qubits, where information is encoded in particles of light, photons. These are especially promising for quantum communication and networking.
What makes photons particularly good for quantum communication compared to the other approaches?
Photons are incredibly resilient. They don't interact strongly with their environment, so they can maintain quantum states at room temperature and travel through optical fibers at the speed of light. Finally, we have topological qubits, still largely in the research phase. These would use exotic quasi-particles called anyons, which could be naturally protected from certain types of errors.
Since they're still in research, does that mean topological qubits don't actually work yet in real quantum computers?
That's right, Sneha. We're currently in what we call the NISQ era, noisy intermediate-scale quantum devices. Our current quantum computers are limited in size and precision, but they're rapidly improving.
So even though they're noisy and limited, can these NISQ devices do anything useful right now?
Absolutely. NISQ devices are helping us explore quantum algorithms, test for quantum advantage in specific problems, and develop better error correction techniques for future fault-tolerant quantum computers. Currently, superconducting and ion-trap qubits are the leading technologies, each with their own strengths. Superconducting qubits are fast but require extreme cooling, while trapped ions have high fidelity but operate more slowly.
Do you think one of these platforms will eventually dominate, or will different approaches be used for different applications?
I believe we'll see different platforms excel in different areas: superconducting for complex calculations, photonics for networking, and perhaps topological qubits for ultra-stable storage once they mature. To summarize, multiple hardware approaches exist for quantum computing. Superconducting and ion-trap qubits are currently leading. We're in the NISQ era with noisy but rapidly improving devices. In our final video, we'll look at the future of quantum computing and its transformative applications in science and technology. Thank you for joining us on this quantum journey.